Alright, I'm Daniel Hubbard, and this is Max, and we're doing one-to-one tutoring, and you realize we're recording you, is that alright?
Yes.
Alright, cool. So let's do it. This is for Organic
Okay.
Chemistry 1.
Cool.
Alright, so it's about chirality, correct?
I think so.
Okay. So let's go ahead and pull out some of your notes, and we'll take a look at where exactly you are in the class.
Yeah, so it's the IUPAC naming,
Okay.
and then, yeah, I guess it's just, like, chirality stuff. So it's like, you would look at it, and then you would be like, okay, so this one's, like, in the back, and then you would...
Exactly.
Like, I'm really good at knowing which one, like, is first, second, third, and fourth.
Mm-hmm. But after
just
that,
really bad at picturing it
Okay.
as to where they are.
Okay, so you realize the theory, though, right?
Yeah.
Okay, so...
Like, it makes sense to me. I'm just having trouble picturing it.
The hardest part is just... Okay, got you.
Yeah.
So... The way I do these, and it's kind of my own method, and it's really goofy, but, okay, so let's look at a molecule, and, alright, so, this guy, for example?
Right.
Okay, so you know that, oh wait, those carbons are the same, right?
Well, they end up being different.
Oh, why? Oh, that one's got a methyl group on it, sorry,
Yeah.
I didn't see that. Okay, so that was first, second, third.
Right.
So, the way I do it is really weird, but like, you know you have to have the hydrogen in the back, right?
Right.
And then you look at it. So, wherever the hydrogen is, I kind of grab it, like, physically in my mind,
Okay.
but like, actually I grab it. So then I grab it, then I rotate from 1, in this case, so the hydrogen's right here, technically. Then I go from 1 to 2 to 3. Okay, so rotate your finger in the correct order. Well, oxygen's here, 2, 3. Now, make the hydrogen in the back and keep your finger rotating with the same orientation to this hand. So make your hand go to the back. Now you're looking at it. Now it's going in which direction?
R. Okay.
There it is. And so it doesn't matter where the hydrogen is ever. If the hydrogen's like in the plane of the paper, grab the hydrogen, go oxygen, methyl group carbon, carbon, and then just rotate. Make sure you keep this orientation together.
Right.
And then, so it's really goofy, and you
Right.
look like a fool in the test. But
That's fine.
like, who looks like a fool once you get the A, right? So.
Okay.
So that's how I do it, and it's never failed me yet. Like, I've spent like hours trying to come up with some method, and like, other than just actually rotating in your mind, that's just the most the best one I've seen.
Gotcha. Okay, quick question.
Yes.
Lined means it's in the back, right?
Yes,
like
exactly.
going into the paper, and then shaded is coming out of the paper at me.
Exactly.
Okay, so like where I get confused, so like looking at this, right? So it's like coming at me, right? So it's like the oxygen.
Yes, exactly.
So it's like here, and then it's like carbons here.
These two carbons?
Yeah.
The carbons are, yes. Yes.
And the hydrogen's like that, right?
Yes, exactly.
Okay.
So, let me see if I can't make that. What is that? So, we will just say that's the oxygen. These guys are hydrogens because there's nothing else I can connect them to. And then we will have, I've never played with one of these guys. These are interesting right here. Okay. This will be the methyl group carbon. And then the red will be our...
I think
The red is definitely an oxygen.
Yeah.
Because, okay, that's our oxygen.
Okay. Cool.
What is this guy then? What's our blue?
Blue would be carbon, right?
Yeah, or something like that. Let's make it our alpha carbon. The carbon that's in the middle. Because we have a lot more black than blue. So that guy is going to be our methyl group carbon.
Okay.
This guy is going to be our hydrogen. Get out of here. And then this guy is going to be our oxygen. And then one more for just a normal carbon.
Right. Okay.
So, for this molecule, your oxygen is coming towards you,
Right.
your hydrogen is going back, and your carbons are in the plane of the paper.
Right. Okay.
So that's all it really is, right there.
Gotcha. And so then you're like here,
This guy
here,
back
here, and you go like that.
Right,
That's
exactly.
all. Okay.
So, and this will work for any orientation. Like, let's say your hydrogen's in the front,
Right.
and your oxygen's in the back, and that's your number one priority. So the way I would do it is in my mind, grab your hydrogen, oxygen 1, methyl group carbon 2, then normal carbon 3, and rotate, and then you rotate it,
Okay.
and then you're still an R. So no matter where your hydrogen is or your lowest priority is, just grab it, rotate, and you got it.
Cool.
So that's like the easiest way to do it.
Okay. So I think I just need to practice those, honestly.
Yeah.
Like, I'll just find some in the book and practice.
You kind of get more used to it after a while. Like, you kind of get to know what it looks like,
Yeah.
kind of thing.
I had something else, too.
Gotcha.
Hold on.
Also, do you know the difference between enantiomers and diastereomers? Because those guys took me forever.
Enantiomers are not are the mirror image, but they don't.
Exactly.
Like, you can't stick one on top of the other.
Exactly.
Diastereomers are not mirror images.
Exactly. You still can't stick one on the other.
Right.
Right. Exactly.
You can stick them on the other and they're the same.
Exactly. Exactly. Yep.
Okay.
That's all it is.
Okay. So we're doing like this thing with nucleophilic substitutions and whatnot.
Got you. Okay.
And I don't understand the difference between SN1 and SN2 reactions.
All right.
And
cool.
E1 and E2
E2.
reactions?
Yes. Yeah. Okay. Cool. So let's go ahead and draw them out.
Okay.
These aren't so much picturing. Do you want to draw them on the whiteboard or on paper? It's up to you.
Draw them on the whiteboard.
All right. Cool. So let me get a marker, and then there's one right there.
Fancy.
Right.
Okay.
So SN1. What does the 1 mean? The 1 means it is a unimolecular. The rate is dependent on one molecule, so it's a unimolecular rate-dependent step. So I'm gonna start with SN2 because that's the most popular one.
Okay.
So SN2. What was the N stand? What does the 2 stand for?
So it's going to have 2.
Exactly. 2 molecules are going to be in the rate-determining step.
Okay. So, like, does that mean that there's 2 reactants?
I wouldn't say that technically. Well, yeah. I mean, there's going to be 2 reactants in all these reactions. You're going to have your main molecule, and you're going to have something coming on or something like that. But it means that there's going to be 2 things determining. The concentrations of 2 things are going to be determining how fast the reaction goes, and you'll see that when you look at the mechanism. So, let's see here. What would be a good leading group? I guess bromine. So let's say I have carbon, CH3, and then carbon, CH3, and carbon, CH3. Okay, so let's just say, okay, so I'm going to do this with methanol, CH3OH. Okay, so I'm just going to go and tell you that the group that's going to get added on is going to be it's going to be the methyl. It's going to be like the carbon part, I think. Is that true? Methanol and right, because that is going to be nucleophilic. So
It's going to attach it to oxygen, right?
right. Yes, exactly. Right. What does that mean? Exactly. So okay. So we're going to have
Like an ion or something?
yeah, exactly. So let's do an iodine right there.
Okay.
And that's a good leaving group, right?
Right.
So what's going to happen is, this is for SN2. This guy is a nucleophile, correct?
Right.
This guy is technically a little bit of a nitrophile, kind of, but what's going to happen is this guy really wants to get put on.
Right.
So actually, I'm just going to have a smaller molecule, not like sterically, but like just for my own handwriting. I'm just going to do Br, negative, because you're kind of done with chemistry. That is, the reactions are going to completion.
Right.
So it's all going to be in equilibrium. So this can go the other way as well. So don't worry about it looking like, well, the iodine can come back on, because it can, and you're right. But just for the mechanism purposes, I'm just going to keep it simple. So this guy is going to do a backside attack right here. Okay.
Okay. So they were saying something about backside attacks. I don't really understand.
Okay. So. Let's see here. Let me draw this with little bit of configuration. So, actually, no, I do want it to be like this. So let's get back to the ball and stick thing. We can take a look at what the molecule actually kind of looks like. So, if we have our carbon, which we'll call this guy right here, and we have four constituents.
Okay.
And we'll call this one our leaving group right here. It doesn't really matter what the other guys are.
Mm-hmm.
So backside attack is when, let's call this guy our nucleophile, okay? So this is going to be set up in the same orientation that's set up, right? So like, let's just say these are our methyl groups, and that's our iodine.
Right.
A backside attack is when this guy really wants to get into a molecule. Mm-hmm. So he's going to come in here, and then boom, attack that guy.
Okay.
And this guy's going to leave.
Okay.
So he just left. He's the leaving group.
Right.
So now these guys are going to get inverted. That guy's going to go like over here. That guy's going to go over there. That guy's going to go over here. And then it's going to be looking like that.
Mm-hmm.
And now this guy just left.
Okay.
And now that was a backside attack.
Okay, so it's just like it rams into one side and pushes everything.
It doesn't really push everything. It's more like it wants the nucleophile, or it wants the nucleus more because it really just wants to like share its electrons. And the leaving group is like, you know what? I'm okay with my electron configuration. I'll leave and I'll take my electrons and I'll be happy. And so then it does end up like moving these guys because
they want to be far away from it.
Exactly, because you know the angle is like 109.5.
Right.
And you want that as your best angle. Exactly. So if you look at the transition state of this, it will look something like this. We have Br, central carbon. Does that make sense?
Yeah.
Br. Does that make sense? Yes. So here is our transition state. And this is where the 2 comes in. The 2 is indicating that we have a bimolecular transition state.
Oh, okay.
Sorry about that. Losing the marker. And that the rate at which this reaction proceeds is dependent on both
BR
concentrations.
and I?
Exactly.
Okay.
Exactly. So if you have a little bit of BR, it's not going to go that much. If you have a little bit of I, it's not going to go that much either.
Okay.
Exactly. So then this is going to end up being no equilibrium arrows because it can go back. CH3. It's going to go CH3, CH3. Let's just say that guy's going to the back. This guy's going to come forward. CH3, and then BR's right there. See that kind of happened?
Yeah.
So now the I is floating off in solution.
Right. Okay.
So, knowing that, what do you think an SN1 is going to be like?
So it's only going to have one constituent, or one thing.
In the rate determining step.
Right.
Exactly.
Okay.
Right, because the speed of the reaction is as fast as the slowest rate.
Right.
Exactly. So knowing that, SN1, a good, very, like the king of SN1 reactions is terbutoxide. That's like, there's other things too, but this guy is like the crown jewel of, if there's going to be one thing, it's going to be this guy.
Okay.
He looks like this. CH3, O, tert, butoxide. CH3, 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 oxygen. Okay, so you can kind of see what's going to happen here, kind of. Okay, CH3, 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 I. Okay, so this guy, what would happen if he tried a backside attack?
Would the oxygen come off?
No. So it would try to get close.
Okay.
But then these are hydrogens coming off, so it's
Right.
so this guy's actually a really big molecule.
Okay.
It's like huge. So like, if the oxygen were to try to get close, the point I'm trying to make is that the space right here that these guys take up won't allow the oxygen to get close enough to do anything. And that is called steric hindrance. When you just have clutter in the way, and you really can't do the reaction you were going to otherwise. If that makes sense. So that's called steric hindrance. So this guy is very sterically hindered. Does that make sense?
Yeah.
So, from there, we know that all we have to do in order to have this reaction go is, if we just take this guy off, we can just put him on there.
Because you just take the eye off?
Exactly, take the eye off,
Okay.
and then put this guy on there, and then we just did the reaction. If that makes sense. Because these CH3 groups are angled away from the iodine, right? So if we take them off, then we'll make them planar.
Right.
And then in three-dimensional space, if that's our guy and we're planar, we can attack from either below or above. Exactly. So, knowing that, let's take the eye off. Okay. Now, what are we going to form? What is this classified as?
Not happy.
Exactly, and why?
Because you never have that.
Exactly. And what's it called? It's a positive charge on the carbon.
Oh, carbocation.
Exactly. Boom.
Okay.
And it would really be unhappy if it was just CH, if these were H's, right? Right, exactly. But this carbocation, we don't have those. They're going to react.
Right.
So, it's going to look like this, and then this guy can attack from the bottom. I guess if this is in the front of the page, kind of that guy or that guy. And then we'll get, sorry if I'm in the way, CH3, 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 and then oxygen. I'm not drawing the spatial because that's not. Yes, that is. What did I do here? That was just right. That was kind of my bad there. CH3. All right, so then we get CH3, CH3, and CH3, and then we just did the reaction. So, does that make sense?
So you stick the entire thing on there? Not just the oxygen?
Yeah, this is actually, sorry about that. So, the actual thing, potassium tetrophenoxide.
Okay.
So you have a K plus there. So kind of like sodium chloride in solution, it's going to dissociate. That guy's going to be in solution, and then so your K plus is over here somewhere, and that guy's going to go on there. If that makes sense.
And then what happens to the I? It just goes with the K?
Yes, exactly.
So you get Ki?
Yes, exactly.
Okay.
And now all of our charges are balanced. Exactly. So, that's SN1. And that actually brought up a really good point right here. So, as far as configuration, like spatially, what can you say in general about SN2 reaction?
So you're going to have a small molecule.
Right.
Like Br.
Right.
And then something else.
Yes, exactly. Exactly. So that guy cannot be sterically hindered.
Right.
And now how about spatial conformation as far as R or S? Like, let's say this guy was an R molecule, for example. Just say, what will the product be? Will it be R or S?
S, because it was backside attack.
Exactly. And that's called inversion of configuration, right?
Oh, okay.
Exactly. Now, SN1, what can you say about that?
So it will be sterically hindered.
Exactly.
And so it'll keep its configuration. Like those R, it'll stay R.
Actually, this is gonna be a big hint as far as what's gonna happen. So let's say your lowest priority was like right down here now. Now it's that way. Now it's your lowest priority is up here, for example. So notice how you can attack from either bottom or top.
Yeah.
So let's say that we have an I coming out here, and and we call that R.
Right.
All right. Now let's say the I is coming out here. Would that be R or S? Exactly. So we can attack from either the top or the bottom, which means we're going to form equal amounts of R or S.
Okay.
And that's called a racemic mixture.
What mixture?
A racemic, spelled like this. Racemic.
Okay.
Racemic mixture. And what that will do, in you know the way to tell how much R to S you have, right? There's only one way to do it. It is you put it into like a device, like the solution, and if you know the length and other numbers, you can find, and you know the angle at which it rotates the plane of polarized light, then you know how much RS you have. Okay, R will rotate it one way, S will rotate the other way. Right is dextratory, and left is another word.
Okay.
I can't remember off the top of my head, but all I know is that right is dextratory and left is the other one.
Okay.
So you cannot. Okay, this is a very common test question, by the way. R and S.
Okay.
You cannot predict whether you're going to be dextratory or the other one's like levitatory, I don't know, something like this. Because of an L.
Okay.
You cannot predict if you're R, if you're this, or you can be either one. If you're S, you can be that. That's the second time. I'm just going to put the top down. There it is. You cannot predict if you're S, you can predict if you're dextratory or levitatory either.
Okay.
So you cannot make that correlation. That's the test question. It's like if you're R, because you know R, you rotate right, so you might think, oh, it's dextratory always because the plane of polarized light goes right. No, you cannot make that correlation. So what it looks like, when you look down the microscope, you're gonna have kind of like you look down like a telescope, for example.
Right.
You're gonna have this guy's gonna be like shaded like one brightness, and this guy's gonna be another brightness, and then you're gonna rotate it until finally you get equal brightnesses on both sides, and then you'll have like a little device on the outside that'll show you like a little gauge right here that'll show you how far you rotated. So that's the only way to really tell between enantiomers how much of each one you have. If you boil them off, they're the same boiling points. For example, if you try to do other stuff, I guess if you have like cis or trans, you can do other stuff. But for like enantiomers, for example, you really can't tell except for this method. So the point I'm trying to get at is that if you have a racemic mixture, what do you think is going to happen to the plane of polarized light? How much do you have to rotate it one way or the other?
You won't.
Exactly.
Because it's the same, right?
Exactly.
50-50.
Exactly. So you 50-50. So it's gonna have a 0 and exactly.
Okay.
So that's
for an SN1.
That's for SN1 exactly. So SN1 you have for a racemic mixture equal amounts of R or S, and it will not rotate the plane of polarized light. So those things go together. SN1 racemic plane of polarized light.
Gotcha.
Does not rotate. All right. So E1. Let's start with E2 because SN2 is popular. E2 is pretty popular.
Okay.
SN1 is less popular, and then E2 is like, or E1 is not popular. It's not that popular either. So these guys first, and then these guys second. Because notice how this guy would try the SN2 first, and then he's got to do SN1 because he can't do SN2.
Gotcha.
So
it's kind of the same thing.
Exactly. So E2 elimination. What do you think is going to happen there?
So there's going to be two things.
Yes, exactly.
Okay.
Yes, and what's gonna happen? What's the final product gonna be looking like in relativity to the reactant? As far as constituents, you're gonna have less, you're gonna have more, you're gonna have equal amounts. Exactly.
Okay.
Because elimination.
Right.
So let's see here. So like, let's say we have BROH. And then we have a molecule that looks like CH3, CH3, 1, 2, 3, ion. Okay? So this guy is very similar to NaOH. And in solution, NaOH is just, to be two separate things, right? So these guys can really do their own things if they want to. So E2 means elimination means, right. So elimination is going to be bimolecular. So what's going to happen is less, right. So the OH is going to do what?
The OH is
onto this molecule. What's it going to do in particular?
Try and replace the I.
Right. It could. And you'll come into the situation in which SN2 and E2 are going to compete as far as what's going to happen.
Okay.
And you might have to determine what's the major product in the reaction. And this is where this gets kind of hard because, right, one thing can happen and so can the other. But it's like, which one's going to happen more? So, like, let's just say this is hot. The E2 is going to be in heat.
Okay.
And why is heat going to favor E2?
Because it gives it more energy.
Exactly. And if you look at the appearance of the graph for any chemical reaction, it looks like this, right?
Mm-hmm.
You have activation energy right here, and the hotter it is, the more you can do that. So E2 has a higher activation energy than SN2.
Okay.
So if you raise the heat, you're going to do more E2s than SN2s, now that's the major product.
Mm-hmm.
So heat. This is going to be hot. So what's the OH going to do as far as, if this is going to be an elimination reaction, what's the OH going to do on this molecule?
Steal the I?
It's going to steal something, but the I is what charge?
Minus.
Exactly, and the OH is also minus. So what's the plus charge that this guy can steal?
A CH. Oh, an H.
Exactly.
Okay.
Exactly. So this is going to be E2,
Okay.
which means we're going to have two molecules doing the same thing. Okay, so this is going to be a pretty big mechanistic step. So the OH right here is going to take the H, and I'm going to draw, these are going to be the movement of electrons, right?
Right.
So CH3, CH3, I. So, where is this electron pair going to go? You tell me.
It's going to turn to a double one?
Exactly. It's going to go there.
Okay.
Now, what about this guy? Now he's got 5 bonds.
Right.
So what's going to happen on that carbon?
It's going to have to drop something.
Exactly.
Okay.
Now, what of these 3 guys is going to want to go away?
The I.
Exactly. So he's going to take the lone pair, right? And so notice how this is looking like one step, and it looks like a concerted reaction, and this concentration and this concentration both matter, because it's just one step. And now what's the product going to look like?
It's going to look like you're going to have the double bond there.
Here, I'm going to let you draw that, if
Yeah,
that's all right.
that seems easier.
Yes.
Yeah, double bond.
Yep.
CH3.
Mhm.
CH3.
Mm-hmm.
You're going to have OH.
Exactly.
And CH3.
Exactly.
Okay.
So,
And then would you have I and Br together?
yeah, exactly.
Okay.
Yes.
Cool.
And that's exactly how E2s will go. So, what's characteristic about an E2? You're gonna have a double bond at the end of it.
Okay.
It's gonna be 2 because you have 2 guys that rate's dependent on.
Right.
So knowing all these 3 things, what can you predict about an E1 reaction mechanism?
So E1.
This is actually the hardest one for me to remember as well. So if that helps.
So you're still gonna have to drop something
Exactly.
because it's an elimination.
Mm-hmm.
And then do you just?
So it's elimination, so you can drop something, you're right.
Right.
Then what does the 1 mean?
I mean, you're only gonna have one.
Rate turning step.
Right.
So it's going to be similar to SN2, but instead of replacing something, we're just going to end up eliminating something.
You mean SN1?
Yeah, what'd I say? Just
Okay.
kidding. Yeah, it's going to be very similar to SN1 in that
Okay.
way. So let me pull up an actual example because SN2 and E2 are popular enough.
Right.
SN1 is like, watch out because of SN2, and E1 is like, let me get an example because E1 reaction. Let's see here. Let's see here. That guy is going to. First thing I clicked on was E2. I'm like, that looks not right. Got it. Okay. So this guy is one of the least popular ones, but it's still important to know because these are your 4 reactions.
Right.
So we're gonna have carbon right here, for example. Let's say these are hydrogens. Carbon. Let's say this is a leaving group. We'll call it I. Hydrogen. What's going to happen here is we're going to form a carbocation, right? Because we have to make it look something like that. So, in this case, the leaving group is just going to leave, okay?
Okay.
So the leaving group is like, see ya, and I'm taking my electrons.
Right.
So, this might not be very stable at all. Actually, it's not stable at all.
Because it's a carbocation.
Right, so let me actually make these CH3s, just because it really should be stable.
Okay.
So, it's carbocation, CH3, CH3. So, we have a base coming in, and this base is going to be like, let's see here, there's going to be R, and I'm going to say O, negative. Okay, we can pretend it was like, something like this guy, for example, or anything else that might, this is true. So, this guy is like, and remember, this guy, alright, let's pretend it's terbutoxide, right?
Okay.
So what can terbutoxide do? SN1, right?
Yeah.
Well, kind of like everything else, that might not be the only thing happening.
Okay.
So like, let's say you have heat, and now let's say like the conditions are slightly different, to where you have SN1 going on, but you mainly have E1 going on compared to SN1. So it's kind of like multiple things can be happening at once as far as which ones, but it's going to be like which one's better. And for the test, they're going to try to make it obvious. It's like terbutoxide is going to be hysterically hindered. It's going to be like at low temperature, so you know it's going to be SN1. SN2 is easy enough to see because it's the most popular one kind of thing. It's just going to be a backside attack, replacing it. E2 is going to be in heat and not terribly hysterically hindered, I don't think. And then E1 might be hysterically hindered, and it might have to be like heat and stuff like that. So that's gonna have to. So they're gonna have to like make it slightly obvious, but know that multiple steps can happen at the same time.
Okay.
And in organic 2, you'll go into a Williams and ether reaction, also known as a competition reaction. So that might allude to the fact that you have E2 going on and something else. Exactly. So this guy's gonna come in and be like, hey, I can take something. I could do that, like I just said, or I can take this guy. This guy's like, okay, you can do that.
Sorry, hold on. So it doesn't want to do that because like it's sterically hindered, right?
Yeah, exactly.
Okay.
And I mean, it could do that, but and we saw it right here.
Right.
And it could do that, but like let's say we have heat once again. And the elimination reactions have this kind of curve.
Right.
So the hotter you get, the more you're going to favor an elimination. Okay. So this guy's like, all right, you can do that. But if you do that, I'm going to drop my electrons off right here.
Right.
So now we get something looking like this. Double bond, CH3, CH3. So you tell me where the difference is between E2 and E1. Start with that. So where's the difference between E2 and
hydrogen there? That's not there, right?
Oh, you're right. Look at you. Awesome. Yeah, sorry about that. That was my bad.
No, you're good. Just making sure. Okay. So wait, the O never actually went on.
Exactly. It just kind of hijacked a hydrogen.
And that was it?
Yeah, that's pretty much it.
Oh, okay.
And then look at your transition step. Or your transition state.
Mm-hmm.
So, what had to happen in E1 in order for us to get here, as far as mechanistic steps?
Well, the I dropped off.
Exactly. That's the third time in a row.
I thought you were just going to leave it on the table.
How did you let me pick it up? I blame you on that one.
That's not even my fault.
Okay, so... Actually, I don't know how I got that in my hand. That's interesting.
I don't remember you picking it up.
Me neither. Okay, so, right, I dropped off, and then this guy had to come in, right? This guy?
Well, yeah, it, like, stole the H.
Exactly. Now, this guy happened all at once.
Okay.
Right? So the point I'm trying to get at is that what's the rate determining step of E2?
So this.
Exactly.
Because both happen.
Exactly, both happen.
Okay.
Now, what's the rate determining step of this guy? Well, I couldn't tell you between the eyes falling off of this guy, but exactly. It's going to be one or the other, and that means that your rate determining step is only going to be dependent on one molecule and not both of them. Exactly. So that's what the SNs mean, substitution. That's what the ones and the twos mean, and that's what the E's mean. So that's basically what's happening as far as SN2, SN1, and E2 and E1. Now, like all of chemistry, the more you do it, the more you're going to get used to it. And it's a lot taken at first, but that's basically the idea going on there. All right, so now you, after all that, you summarize each reaction type.
Okay. So SN2, you've got backside attack.
Exactly.
And it, like, kind of knocks one of them off, and the other ones just kind of shift.
Exactly. And what's going to happen to your...
It switches.
Exactly. It's going to be an inversion of configuration.
Right.
Exactly.
Okay.
All right?
SN1, it, like, tries to backside attack, and it's like, oh, wait, I can't, because there's too many things in the way.
Exactly.
And so then you just have one of them fall off, and then you have it attach.
Exactly. And what's going to happen to your configuration?
It's going to be 50-50.
Exactly. Exactly.
E2... Hold on. E2's elimination, so, like, it's going to steal something, and then something's going to fall off, and it's going to attach.
Yes, all at the same time.
Right.
Exactly. It's going to steal something, and while stealing something, it's going to push the electrons down onto the double bond. Then the carbon is going to be like, oh, I have 5 bonds. Somebody's got to leave. And the best leaving group's going to leave. It's going to look like that. And that's exactly right.
So it's like... So, like, if I'm looking at this, I'm going to be like, okay, this wants that H.
Yep.
Which means these go onto here.
Exactly.
Which means that has to leave.
Exactly.
Okay.
And it's interesting enough that all that is going to happen, like, in one plane.
Right.
All right, you knew that? All right, cool.
Wait, so, like...
So if you look down it, you can see, like, if you look down it, you can see the O, attacking the H, put on the double bond, and the I's going to fall off. So it's, like, all happening in one plane.
Okay.
Does that make sense? So it's not like your O is going to attack over here, now your hydrogen's going to put over here, now your iodine is going to fall off over there. It's going to happen, like, in one plane. So that's just kind of an interesting fact. I'm not sure if that's going to be important.
Right.
It might be, but that's just kind of what happens.
Okay.
And then E1.
So then E1, it's going to... Something's going to fall off.
Yep.
And then it's going to come in and steal something, and nothing's actually going to attach.
Exactly. Yep. And then you're going to form your double bonds.
Sweet.
Yeah, so that's exactly what happens with SN2 and SN1 and E2 and E1. And for me, okay, so I didn't really know how to do organic chemistry in the first place. Like I didn't know how to study for it. So I came in to organic chemistry doing all right, and then I got to this guy's, and I'm like, all right, it's fine. I'm okay still. And then I got to the next chapter, and I'm like, well, hold up. I'm getting a little lost. And then I realized it was because I didn't really know what was going on here.
Okay.
So this was kind of like the number one hard thing for me, to understand which reaction mechanism is happening where. And then other chapters start falling into place.
Gotcha.
So once you kind of like get this heavy lifting out of the way, you know what's happening here, things will fall into place later.
Okay.
All right, cool. So that's those 4 reactions. Is there anything else about those reactions or anything else currently in this chapter that are important and problematic?
I was a little bit confused what this was talking about.
Okay, so okay. Yes, this one took me halfway through Organic 2 to actually realize. Basicity versus nucleophilicity. Okay, so what?
It's like... I understand, like, whether it's primary, secondary, tertiary, etc. Like that's whatever.
Right.
But I don't know.
If something's a good base versus it being a good nucleophile?
Yeah.
Okay,
and what is the difference between a base and a nucleophile?
Okay, so let me ask you, what's a base? Just by acid
like a
base
Lewis
chemistry.
base?
Yeah.
Lewis base wants to donate electrons. Right?
Exactly. Now, in acid-base chemistry, normally bases pick up a what? Let's say Bronsted-Lowry chemistry.
A nucleus?
Exactly, a hydrogen, an H+. Now, nucleophiles, what's the definition of those guys?
They want a nucleus?
Exactly. Exactly. So, let's say that we have a guy that's just like, hey, I don't mind donating my electrons. So he's on a right base, but let's say he's pretty fat, kind of like SN, like kind of get on SN1. But oxygen's like, hey, I'm a good. Let's see here. I don't mind taking a proton, but actually it's kind of good both. It's actually really hard to find a good example. My point is that I'm trying to say is that sometimes you can donate your electrons better that you can get onto. A nucleus, exactly.
Oh, okay.
Does that make sense?
Yeah.
So, because he's not that... It actually is pretty good once you do an SN1 mechanism, but he's not the best at saying, hey, I can get right on you because I can get right close to you because it kind of can't. But, yeah. Exactly. So, and that's kind of why they both correlate, is that basicity is like, I want to give my electrons, and nucleophilicity is like, I want to get onto a nucleus. They kind of go together, but one's like...
One wants to attach more.
One wants to attach, and one wants to get rid of the excess electrons. So, like, they want similar things, but if the molecules are made in a certain way, they can, like, sometimes not be that good at one or the other. That's like the basic summary. The best way to do this is find an example, but let me see if I can. Basicity versus nucleophilicity. Increasing base. Nucleophile. Nucleophile. Increasing. Okay. Increasing basicity. Okay. Okay, that makes sense. Alright, so kind of like this chart is kind of showing you. So let's compare F negative and I negative.
Okay.
When in solution is F negative happy? Do you ever see that F negative floating around?
No.
Exactly.
See I negative floating around more.
Exactly. And so now, what would that mean as far as how much they really want to be attached to something?
Oh, so then the F is a better nucleophile.
Exactly.
Because it never wants to be by itself.
Wait. No, it's a better base. Sorry about that. That was totally my bad. That was a loaded question. Okay. Using nucleophile. It's a better base because it wants to give away its electrons.
Okay.
Much more than the I wants to give away its electrons. That makes sense. So the I is happy with its electrons.
Because it floats alone.
With electrons.
Okay.
Exactly. And the fluorine doesn't like to have all the electrons. So it really wants to give it up. Now, they're both really good nucleophiles and bases.
Right.
So it's kind of a really gray area. But the fluorine really does not want to hold on to its electrons.
Okay.
So it's a better base for that reason. And then as far as nucleophilicity, they have I being better at that because it's actually a really good question. I think these are relative to each other. Is kind of the point.
Okay.
So like fluorine really wants to give up electrons more than it really needs a nucleus, and then iodine really is okay with having its electrons, even though it would take a nucleus.
Okay.
That makes sense.
So it's more just like a sliding scale.
Yeah. So it's really like a gray area, and if you have a question on that, it's gonna be a really hard question, and most people are not gonna kind of understand what's the difference. But that's kind of the difference.
Okay.
And even I have trouble with it sometimes. So once again, the more like you kind of get to know, like, oh, you don't see F negative floating around, it's gonna be like, okay, you kind of putting the parts together. Oh, let me go back to that chart. Interesting. Okay. And then I guess CH3 is just a really good base and nucleophile because you never see that guy floating around. That's like the worst thing to be floating around like ever.
Okay.
So
that makes sense.
Right. So yeah, I guess this is the best one to see the differences because here they both increase. So that's not the best trend. But I guess those trends are more important. So I guess if you remember these trends, they might be able to help you out. Like
somewhere on the test, possibly.
Exactly.
Okay.
So, yeah. And have you been given a chart of nucleophiles or leaving groups?
No.
Okay. Well,
I think she said we might get one. A chart of leaving groups.
Okay. Good. Yeah. Because like a common thing I have is like, well, you know, I as a good leaving group, you know,
right.
But, like there's like a gray area. There's always a gray area with chemistry. So it's like, is that a good leaving group? Well, I'm not sure. So sometimes like. A chart might be handy.
Right. Okay. Cool.
So go ahead.
Okay, just this question.
Right. Okay. So let's see here. Should put in the middle. So in class problem, for each of the following pairs of reactions, which one is faster, A or B? Okay. Okay, so this guy in the middle is just a solvent, right? You don't see him in the reactants or products, so it doesn't really do anything. Okay, so this is exactly why we need a leaving group chart. Okay? Because whichever one is happier being by itself is not going to really seek out replacing somebody else. So,
but it's the same leaving group.
Is it? Oh, so the only difference is
the solvent.
Is the solvent. Okay. I read that wrong at first. Okay, so that's a good question. So what's floating around solution? What is that, an I negative?
Yeah.
Where'd that come from? It's not in any reactants, nor is it in the solvents. Okay, that's interesting. They got an iodine. They made iodine from somewhere. That's interesting. Okay. So CH3 is going to be on that guy. So, okay. So I would just draw the solvents and take a look at what they look like. I'm about to erase this right here. So the first one is methanol, which is simple enough. Oh, the next one is this guy. That's correct, right? No, it's not.
No, I think the CH3 is attached to that.
Would that make sense? Wait, can I say it again? CH3. HCl.
Right.
I think the CH3 is going to be attached to the nitrogen because otherwise they would write the CH3 right next to the oxygen.
Oh.
I'm checking my bonds correct. Because carbon's got to have 4 bonds. Wait, yeah, carbon's got to. How's carbon gonna make 4 bonds from there? Let me type that in and see what Google has come up with. Because I'm not sure if I can get a good Lewis structure for that guy. So it is going to be HCON.
CH3.
HCON. CH3. That's a hashtag. Came with seashells. Yeah, see, I feel like there should be a 2 subscript there to make everything work out right.
You think it's just wrong?
Well, let's just say that there's a 2 subscript there, because I don't see how they would otherwise make a good load structure with that. Plus, I'm not sure I have much faith in this question anyways, because they made iodine. From somewhere. From somewhere.
Right.
So... that makes sense right there. Okay. So... you right. Alright, so... yes, you're right. So then we have to determine how fast SH1 is going to replace, or SH negative is going to replace BR negative.
Right.
So which one has hydrogen bonding going on?
The OH.
Exactly. That's got hydrogen bonding. This guy is going to have... a beer table. Alright, yes. So look at sulfur on the periodic table. It's right under oxygen.
Okay.
So that means that it's going to be electronegative, which means it's going to do that, which means it is not hydrogen bonding. It's pretty darn close. So what happens when you have likes? Like dissolves like? Right? That's just kind of like, that's what I'm trying to say.
Yeah.
So this guy is pretty polar, and this guy's pretty polar with hydrogen bonding going on. This guy's going to stay in the solution longer.
Okay.
So, if he stays in solution, what's he not going to be doing?
Reacting.
Exactly. So, this one should react faster, because you don't have any of that hydrogen bonding. If that hydrogen was attached to the oxygen, things would be different. But this hydrogen is attached to the carbon, and so hydrogen bonding can't really happen as much. So... for this reason, this guy should come out of solution and then react.
Okay, that makes sense.
That's what I thought. Do you know what the answer was?
Yeah, it was that one.
It was that one?
Yeah.
That makes sense. Cool. So, yeah. So, chemistry. When in doubt, draw it out.
Okay.
Also, you're not going to be able to make any iodines from...
Yeah, I don't know where they got iodine from.
Alright, cool.
Cool.
Thank you very much. And
Thanks,
it was
Danny.
definitely nice.
Can we do a handshake?
Yeah.
That's great.
Look at that. Look at that.
Oh
there
my
it is.
gosh.
just a random hand coming out from the side. That's
I feel
awesome.
like being actually filmed.
Can I hold this now, finally?
You can hold it now.
Yes.
I'll allow it.
Alright, thank you.
You probably want to put it on.
You're right. Alright, well, it was definitely nice. And all you have to do is go to the iPad, select your name, do the survey, and you'll be signed out.
Cool.
Alright, and I'll see you sometime later, hopefully. Alright, bye.